In this video, I will present an introduction to functional approximation. The objectives of this module on functional approximation is for you to understand first the difference between type of approximation and criterion of approximation, and to understand also different functional approximation criteria such as interpolation or least squares. And finally, the basics of sectional, or also we call it piecewise interpolation. All of these also make you able to select a proper approximation criterion for a given case. So if you have an application, then what is the best or proper approximation criteria for this case? Then you will be able to also compute the interpolating polynomial that passes through a set of points. Okay, and finally you will be able to state and solve least square problems. We will talk about least squares also in this module for parameter fitting. The main goal of functional approximation basically is to obtain an approximation that we call it px of a given function. So if we have a given function of f of x, then we want to approximate this function with another function of px. So in many engineering applications, basically we need to compute a functional approximation, and then the selected method for the functional approximation depends on the following factors. So first, what we know about the function that we want to approximate. So basically the knowledge about fx, whether fx has an analytical expression, or we have some values of this function at a given set of points. Okay, so we have maybe n points of this function that we know the value or its derivatives, and then based on this data we want to approximate the function px. So the information about fx is important, and also we need to know why we are approximating basically the function of f(x) with px. So we need basically this approximation for computing integrals and derivatives. Suppose that you have a set of data from f(x), but you want to compute an integral of this function, an approximation function, or derivatives on certain points. Then you need an approximation for this set of data, and also the value of the function or derivatives at certain points. So for example, if we want to get the value of this function for other points that we don't know, then we approximate, and then we can obtain the value or the derivatives of the function at any point that we want. Let me give you some examples on applications of functional approximation. The first example is on interpolation. Here we have the values of a function at a finite set of points. This finite set of points we represent it by xi and fxi, and then we need to determine the value of the function at any arbitrary point. Okay, so here we give you an example on motion capture. So basically, if you put sensors on the body of humans or animals, then you can basically capture the motion of each point, and finally describe the motion of an object as a function of time. So using a finite number of measures that we get from these sensors, then we can do this functional approximation. So here in this graph is an example. So assume that we put a sensor on the body of a horse, and then we capture the location of this point as a function of time. So basically we have some data points at different times. Okay, and now we want to approximate a function from this data point. So basically the red points here are the points, the finite points that we get from sensor. So the position, the location of the sensor at different times. And now we do an interpolation. So this basically, this blue line is interpolation, a function that passes exactly through the points. And now we have a continuous function as a function of time. Okay, this blue line. So now we can obtain the location at any point that we want, because this interpolation basically is a continuous function. And for example, at time 2 that we don't have any data, since we have an interpolation, we can get the position. Okay, for example, in other point such as 5 also we can get this position from the interpolation. Okay, so any point that we want, we can get this because of the functional approximation or interpolation that we obtain. Another example of functional approximation is linear regression, and here we want to determine the material parameters from experimental data. As an example, you consider a spring that you attach some weights to the end of this spring, and then basically you are applying a force to the end of this spring. So by increasing the weights, basically the displacement of a spring increases. So the displacement here, d, you can plot it as a function of f, and this points, these black points, basically is your measurement. So you measure the displacement by increasing the weights or the force. So since you cannot do these experiments for all the forces, then you can fit a line to this data. Here we call this fitting linear regression, and in contrast to interpolation, this line doesn't pass exactly through the points. Okay, so this is an approximation of the points that you have. And after fitting this line, then you can obtain a line, the formulation of the line, where you can obtain your displacement as a function of the force that you apply. Okay, so you give some force here, and then at any force you can obtain the corresponding displacement. You can rewrite this equation, and you can write the line based on F, force, as a function of the displacement. So here in this equation, you give any value of d here, and then you obtain your approximated force. Okay, so basically from this equation, then the slope of the line here, the slope of the line where you have the line expressing the force, then this is the stiffness of the spring, which is 21.3. So in conclusion, by linear regression or fitting a line, you can obtain the equation of the line, and the slope of this line basically gives you this stiffness. Okay, and this stiffness is a material parameter that you can obtain from linear regression or functional approximation. Here I present the basic concepts behind functional approximation. As I mentioned before, our goal is to approximate a function f by another function p in an interval between a and b. So mathematically it reads p approximates f. Two basic ingredients are required to define an approximation method. First is the type of approximation, and another is the criterion of approximation. For the type of approximation, we would like to know which type of functions p are going to be used to approximate f. That is, in other words, we want to select the function space for our approximation. Regarding the criterion of approximation, basically we want to answer this question: what does px approximates f mean? Because the symbol of approximation can have different meanings, and based on the meaning of this approximation, then we can identify our approximation method. Regarding the first ingredient, the type of approximation, we have different types. The most commonly used one is the polynomial approximation, as you can see here. And this is because their derivatives and integrals are also polynomial and easy to compute. The second one is trigonometric approximation based on cosine and sine terms, and it is commonly used for periodic functions and signal analysis and partial differential equations. We have also exponential approximation based on exponential terms, and it is used for approximation in signal analysis and also PDEs. The rational functions basically is defined based on rational fraction, and it is used for approximating functions with asymptotes. An asymptote is the line that when a curve approaches that line, the values goes to infinity. So this line then is then asymptote of the curve. So for approximating functions with asymptotes, then we can use rational functions. The last one is the piecewise functions, when you have different approximations for piecewise sections between points. So you have different approximations for each of these 2 points, and it is usually used for lower order polynomials. The second ingredient of approximation methods is the approximation criteria. The first criterion, we call it interpolation. And for interpolation, we assume some data points fxi for n+1 points, and we impose the equality of the approximation and the original function for each point. Okay, so this equality is very important in interpolation when we have to satisfy that. So in this curve, we show this graphically. So imagine that we have an original curve of original function of f, the blue one, and the interpolation of p. So the red one is the interpolation over the points on f. Okay, you see that the red curve, which is the interpolation, exactly passes through the points and reproduce exactly the value on each point. So in all these points, px equals to f. But between the points, there can be a gap. Okay, as you can see here and here, there's a gap. So we can also prescribe some conditions also on the derivatives. In addition to the value of the functions, we also prescribe equality of derivatives. In this case, Taylor polynomials are a particular case which satisfy the equality of derivatives. Here is the equality of derivatives, and this k basically is the derivative order. For a Taylor polynomial of degree n, basically we can satisfy or we can prescribe the equality of derivatives until order n. Okay, and here you can see a Taylor polynomial which can be written in this form, and as a function of the value of f and derivatives until degree or order n. The second approximation criterion is least squares, and the idea behind least squares is to minimize the distance between the data f and the approximation p. This minimization is equivalent to minimizing this functional. This norm is called Euclidean norm, or the distance between p and f. And if we minimize the square of this norm with respect to p, then we can get our approximation. In the case that f and p are both continuous, then this norm is defined as this integral term, and it is basically is a function of the area between p and f, all these areas. And if we sum all these areas and minimize the total area, then we can come up with our approximation P. In the case of having data points or discontinuous information, then this norm is defined as a function of this sum, and it is basically the sum of the distances between the data points and the corresponding points on the approximation. So all these distances, the red lines, basically you sum and you minimize the total distance, and then you can come up with your approximation P based on least squares. The third approximation criterion is the min-max approximation. The idea behind this approximation is again to minimize the distance between the data fx and the approximation px, but here instead of using the Euclidean norm, we use the L infinity norm. So the minimization can be stated as this, and basically here we are minimizing the L infinity norm of a distance between f and p, and I recall that the L infinity norm is the maximum distance between f and p. Okay, and why we call this approximation min max? Because we are minimizing the maximum distance between f and p. This is why we call it min max approximation. So consider that we have some data points and we want to approximate these data points with the function p. Okay, so if we obtain the distances, so the first distance, the second distance, and the third distance. So here it is obvious that the maximum distance is the last one. This is the maximum distance. And then if we try to minimize this maximum distance, basically we are minimizing this distance. Basically we come up with our approximation. So a drawback of this method is that it is very hard to compute, and also I would like to mention that the least squares approximation is similar to the min-max approximation when appropriate weights are used. So consider that you multiply some small weights to the first and second distance. So you multiply some small weights or small numbers to these two distances, and if you do this, then when you sum these distances in the least squares approximation, basically these distances becomes very small because you are multiplying some small numbers to these distances. So finally in the least squares you are focusing more on the last distance, which has more weight, and this is becomes very similar to the min-max approximation, which also focuses on this last or the maximum distance. In this slide, I would like to introduce Weierstrass theorem. This theorem establishes the goodness of polynomials as approximating functions. So you remember that we discussed polynomials as one of the most used type of approximating functions. So this theorem says that if we have a continuous function of f in the interval between a and b, and for any parameter epsilon which is positive, then there exists an integer number n that depends on this epsilon. So basically we can write n as a function of epsilon such that the difference between f and p is always less than epsilon, and this condition holds for any value between a and b, where this n is the degree of polynomial p. Okay, so this epsilon we can call it accuracy, And basically this theorem says that any continuous function f can be approximated by a polynomial p to the desired accuracy of epsilon. So by choosing a polynomial, you can reach a desired accuracy, okay, as small as you want. But be careful that this theorem does not describe how to choose the polynomial degree. So the choice of n, this theorem basically doesn't have anything to say about this choice. And also this theorem doesn't say how to compute it, okay, how we can also obtain this polynomial degree. So this is the basics of Weierstrass theory. This is a graphical representation of Weierstrass theorem. In the first graph, you see a polynomial approximation of the blue curve. The red curve basically is a polynomial approximation. And in this case, you see that the approximation is not good. And the difference between the approximation and function is always less than epsilon 1, okay, which is a relatively large number. So this approximation, we can say that this is not good, okay. But by changing the polynomial degree, change n, which is the polynomial degree, then you can obtain a much better approximation. So in this case, the distance between the approximation and function is always less than 0.25, which is a smaller number than 1. So in this case, we can say that this is a good approximation. So basically this epsilon shows the goodness of our approximation. This is another example on the right. Again, the approximation is not good, and the distance between the approximation and function is always less than 1. This is not good. So but again, by changing the polynomial degree, we can obtain a much better approximation. And here again, we can say that the difference between the approximation and function is always less than 0.25. And based on this, then we can say that this is a good approximation. So basically this epsilon again shows the goodness of our polynomial approximation coming from this Weierstrass theory.